Okay. So before we move on, any questions? Okay, hopefully people are interested in this problem. So I'm going to talk about RowHammer because I think this is really fascinating. And as I mentioned, we follow 4 key directions, and this really falls into the secure, reliable, safe. Security, reliability, and safety clearly are different things, but RowHammer is a place when you get bit flips, you have all 3 problems basically, and you can exploit it for security. You can clearly, it's a reliability problem, and it can actually affect your safety also. So as I said, basically, this is the problem that you can predictably induce bit flips in commodity DRAM chips. And when we actually did the studies in 2012 to 2014, we found out that more than 80% of the tested DRAM chips are vulnerable. These are chips that you can buy off the shelf. And this is really, as far as I know, the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. If you know of something else, please let me know. And that's why people are writing things like this. I'll motivate this from a psychology perspective a little bit. How many people know who this person is? Yes, there's a side channel here. It's Maslow. Actually, there are multiple side channels. It's Abraham Maslow. He's a very famous American psychologist. And he's known for his work on understanding why people, or trying to understand why people do the things they do. He's probably more well known for this hierarchy of needs, which is really used in many areas, like economics also, sociology. But basically, what this says is, if you want to really think about higher levels of achievement, like self-fulfillment, like higher levels of abstract art, you need to have your basic needs satisfied first, right? Your physiological and safety needs. That's why we really need to start with reliability and security. And when I motivate this to freshmen, actually, I teach some of this to freshmen, I also talk about this bridge. There's a side channel over here that I can cover. Does anybody know where this bridge is? Yes, it's Seattle, Tacoma. Actually, I will argue that this bridge doesn't exist because this is what happened to that bridge. So this bridge was over the Hood Canal in 1940 when it was built, but it got a bit flip, and this is what happened to it. It's clearly not a bit flip, but it's really aerostatic flutter, and there are a lot of interesting studies on this, which I'm not going to bore you with. But this is an example of critical infrastructure having a reliability problem which is affecting safety and security at the same time. And you could imagine other examples of this also. And we're building hardware infrastructure for the world going into the future that's going to be even more important than this particular infrastructure, in my opinion. If you have DRAM that's employed in all of the intelligent agents or even non-intelligent agents everywhere in the world, if you have this sort of bit flips everywhere, it's not going to be a fun world to deal with. Basically, all of the safety, security, and reliability will be compromised. So this is, I think, not so bad compared to what we're going to deal with going into the future if we have similar issues in hardware infrastructure. Okay, I like this also. That's another example. These are folks building New York after World War, and basically they're happy. They're sitting on some critical infrastructure, critical to them at least. But if they get a bit flip in that infrastructure, they may not be happy soon, right? Basically, I think of security as preventing unforeseen consequences, and I think going forward, it's really good to think about it this way. This is very general, of course, but if you think about it this way, maybe you can provision for some things that you put into hardware or software to actually prevent some of the things that you haven't foreseen. Okay, we talk about the DRAM scaling problem. I'm not going to talk about it again. Basically, as the storage unit and the access device becomes smaller, DRAM becomes more vulnerable. And we already seen evidence from the field. And we actually knew this much earlier than we started working on RowHammer. Clearly, we didn't do these studies before RowHammer, but we were doing it concurrently. Okay, so we were building these infrastructure where we could test memory to understand some of these reliability issues, because clearly reliability is the problem. So we did a lot of retention testing, which I'm going to briefly talk about, because in the end, I think the really big limiter of memory scaling is retention. How much you can retain data in a DRAM cell. And how do you figure out how often you should refresh this DRAM cell? That's really a fundamental and tough problem. I think RowHammer is a very important problem. It can be solved, and going forward, it's going to be much more difficult to solve RowHammer, but retention is even harder, perhaps. Okay, while we were doing all these studies on retention, we actually built infrastructure, and we asked the question, can you actually have these read disturbers in DRAM also? And clearly, you know about this infrastructure right now. So let me talk about the retention studies very quickly. So today, as I said, DRAM is self-refreshing itself. It's refreshing itself every 64 milliseconds right now. Actually, if you have a later iPhone, it's refreshing itself every 32 milliseconds. Because things have scaled and you need to refresh more frequently. And that's kind of a waste, right? So we said, maybe it's not a good idea. Do you really need to do this, basically? Do you really need to refresh every single DRAM cell every 64 milliseconds? And basically, if you look at the retention time of distribution of DRAM cells, it looks like this. Most of the cells, you can get away with refreshing every 256 milliseconds. There's a very small fraction of cells you need to refresh every 64 milliseconds. This is because of the nature of process variation, and different cells have different retention times. And if you actually know this retention time distribution, if you expose it to someone, it could be the memory controller. If it's the memory controller can say, okay, I'm going to refresh different cells at different rates. Now you've gotten rid of almost 75% of your refreshes, right? Yes. Yes, we're going to talk about that. Does it change with aging? So with aging, not so much, actually. But with time, there's a different dimension, which I'm going to briefly talk about. Okay. So this is actually depend on location, clearly, right? Different locations have different retention times. This may, it's depend on stored values. It's depend on time also. It's depend on time in the sense that, one cell may have a retention. Actually, most DRAM cells are extremely strong. If you take out the DRAM over here and soon, if you put it onto some other computer, you'd be able to read most of my DRAM actually. And people devise cold boot attacks. They actually do it. On top of that, they freeze the DRAM, and they can retain the data, of course, much longer at lower temperatures. So most DRAM cells can actually retain data for hundreds of seconds. So why are you refreshing every 64 milliseconds? One of the issues is this time dependence. Basically, this is called variable retention time. You may test memory at this point in time. The cell retains data for 100 seconds. Let's say you test it 100 seconds later. You may find out, to your surprise, that it retains data for only 64 milliseconds. Why? This is actually a circuit level effect. I call this a quantum-like effect in circuits. Basically, randomly, as far as we know, this is a purely random process, and the data suggests that it's purely random. Randomly, charge gets trapped in the access transistor of DRAM cell. Not always, at random times. And when charge gets trapped in the access transistor, what happens is capacitor leaks much more quickly. This is called trap-induced gate-assisted drain leakage. Trap-assisted gate-induced drain leakage, sorry. TAGIDL. And this happens randomly, and people have tried to model it, but there's no way of modeling it, so there's no way of predicting it. As a result, you have to be conservative. So if you really want to understand how often you need to refresh a memory cell, you need to do online profiling, online testing, essentially. So over time, you test the DRAM cells to figure out how often you need to refresh. Okay, so, but if you do that, if you figure this out, and I think it's possible, then you can get a lot of benefit. You can actually reduce the refresh rate by, let's say, almost 75% over here, right? And that's a lot, actually. And we've been doing that. That's the reason why we built the infrastructure that I showed you, actually, to understand these retention times. We knew that these retention times were like this, because there's a lot of literature that talks about it. But how does it look like in real systems? And in real systems, with the infrastructure, we did a lot of studies. And we basically said it's not easy to do this retention time profiling for data pattern dependence and variable retention time. And we wrote a lot of papers. If you're really interested, this is a fascinating topic also. How do you actually overcome these data-dependent failures? How do you actually take advantage of the memory content to reduce the testing overhead? How do you actually profile for these failures as much as possible? And this is one of the most recent works that looks at recently, actually, DRAM manufacturers starting adding error-correcting codes in DRAM chips. And if you really want to know the real reason for that, that's variable retention time. Because they're not able to figure out the minimum retention time easily for every single cell. They actually wrote that in the Samsung and Intel paper that I mentioned. They basically said, okay, we're going to give up. We're going to add error-correcting codes inside DRAM. And this is actually, this was a taboo area for DRAM for a really long time. All of the other memories have error-correcting codes. Like flash memory has extensive error-correcting codes because flash memory doesn't even, most of the flash memory bits don't even work when you manufacture them. You have to error-correct them. DRAM, because it's so cost-sensitive and the mindset has been so commodity, people didn't want to add error-correcting codes. But now they have to add error-correcting codes because this variable retention time issue has become much worse. Actually, our results show that variable retention time, the amount of cells that are subject to variable retention time is increasing. And sometimes you need to test for days and days, like 3 days or 4 days to discover a cell's minimum retention time. Yes?
Is the test is destructive? Can you test while storing?
No, it's destructive, yeah. Basically, you can do online profiling, yes, but you need to be extremely careful because you need to move the data somewhere else. And you cannot do this test, actually. So you can say, OK, why are you bothering me with this? This is the manufacturer's problem. Maybe you can think again. Basically, the DRAM manufacturers actually manufacture DRAM chips. You take the DRAM chip and you solder it on a DIMM or a board. Whenever you do the soldering, you subject it to high temperatures, let's say 300 degrees Celsius. Now, those high temperatures actually change the retention time profile completely. So a DRAM manufacturer guarantees something to you, but that retention time profile changes. Which means that they don't really guarantee fully anything in the end. They add a lot of margin to guarantee things. So imagine we're using these chips in critical infrastructure. OK, anyway, so there's a lot of fascinating things. So while we were doing these studies, we also asked the question, are there other types of errors we can induce in DRAM? Clearly, refresh errors we can induce as we increase the retention time, refresh interval, right? But we were also doing a lot of studies on flash memory, and we were also working with Intel quite a bit on memory controllers. And in flash memory, if you look at that, one of the error mechanisms is read disturb. Whenever you read a page, you disturb the contents of other pages. Little. And if you keep reading a page over and over, you disturb the contents of the probability that you disturb the contents of other cells increases in flash memory. And flash memory controllers provision for this, and they add a lot of error correcting codes and other mechanisms like voltage optimization to avoid this as much as possible. We asked the same question, can you actually do this in DRAM? Because this becomes a big issue as you scale flash memory down to smaller technology nodes. We had a similar infrastructure for flash to test it. Since we had the infrastructure for DRAM for retention time, we basically found out you could actually do that in DRAM also. And as I said, it's the RowHammer problem. It's this problem that I just described, basically. It manifests itself in a slightly different way. Basically, memory consists of rows, DRAM memory. And if you want to read data from one row, you need to open or activate that row, apply high voltage to that row. If you want to read something else, you need to first close this row, meaning you need to apply low voltage to that row or pre-charge the array. This is called activate and pre-charge, high voltage, low voltage. Now, if you keep doing this repeatedly, high voltage, low voltage, high voltage, low voltage, activate, pre-charge, activate, pre-charge, activate, pre-charge, activate, pre-charge, enough times before the memory gets refreshed, it turns out in some DRAM cells, you can induce these bit flips. And these DRAM cells happen to be physically adjacent to the row that you're activating repeatedly. So why is this happening? It's essentially disturbance. There's electrical interference that's happening between this row and this row. Things are not isolated enough from each other. Whenever you're activating, you're causing some disturbance over here. It's actually a complicated mechanism, but I have some slides. I'm going to skip them right now, but I'm going to explain them. But basically, whenever you think about it this way, if you're activating this row, you're applying high voltage. Since this word line is not isolated, you're applying some high voltage to that word line a little bit, which means that these cells get connected, capacitors get connected to the bit lines, meaning that they lose charge by little. And if you keep doing this activation many times, enough times, before the cells get refreshed, some of the vulnerable cells lose enough charge that they are depleted. Basically, you cannot recover the charge anymore because they're not refreshed early enough. You've done too many activations next to those cells, basically. So this is a read disturbance problem. This actually exists in all types of memories. In a sense, it's not surprising that it happens in DRAM, but it's a bit sad that it happens in DRAM because DRAM is everywhere, right? And there's no correction that happens in DRAM. So we call this the hammered row. We call these the victim rows. And we showed that more than 80% of the chips that we've tested from 3 major manufacturers, and in DRAM there are only 3 major manufacturers, A, B, C. You can guess who they are. Basically are vulnerable to this problem. Actually, the numbers are even larger because of what I'm going to describe in a little bit. We didn't really have the best RowHammer attack to these memories. Later, people have developed different RowHammer attacks that could actually induce more bit flips in your memory. So this is also a scaling problem because the chips that we tested that were manufactured before 2010 did not have this problem. The first occurrence in 2010. Basically, the way I like thinking about this is the cells got too close to each other in 2010 that you could do enough activates to induce these bit errors in a refresh cycle. And later on, all of the chips that we've tested that were manufactured between 2012 and 2013 were vulnerable to this problem. You may ask, why is this chip not vulnerable? Maybe our test was not good enough. So the way I'm going to talk about this in a little bit, but if you actually have a better test, this chip actually may have an effect. Actually, that's an open issue in RowHammer, in my opinion. How do you actually quality assure a memory to be not vulnerable to RowHammer, or even a single row to be not vulnerable to RowHammer? That's an open question. Okay, so why is this happening? I've already talked about this. I'm going to skip this. Clearly, this has higher-level implications because this bit flip affects the upper layers of the transformation hierarchy, right? This bit flip gets exposed to the data structure and your program, and this bit flip, if it's predictable, if you can induce it over and over, it could be a security problem also. And we showed that actually you could do it at the user level. So this is a user-level assembly program, 6 lines. Later, other people eliminated this M-fence, rightly so. So you could actually do it in 5 lines also. But basically, this program, what it does is it selects addresses X and Y such that they map to different rows in the same bank. And they basically ping, it avoids cache hits, clearly. It avoids row hits so that you basically keep hammering these 2 different rows. It basically ping pongs activates. I should do it this way because my latency to my USB is, okay, let me do it. This is a problem where USB latency or this communication latency is too high, at least at this point. Yeah, basically it does this. And if the chip is vulnerable, it'll get errors, of course, subject to the fact that this is the best attack we designed. So later, Google actually took our code and used an observation that we have in our paper, and intelligently what they did was they basically selected X and Y such that there's only 1 row sandwiched between X and Y. And once you sandwich 1 row between X and Y, you have a lot more errors easily. This is called double-sided row hammering. Okay, and these are our results. Later results actually are much more effective. Basically, these show that you can do this on real systems. There is nothing special about Intel and AMD. Any memory controller actually, any commercial memory controller is good enough to do it. Even non-commercial memory controllers, if you take off Xilinx's memory controller, for example, that you can put on your FPGA, you should be able to do this hammering. And on a vulnerable device, you should be able to get errors. Okay, this is a reliability and security issue. And when we first wrote the paper, basically we said that memory isolation is a key property of a reliable and secure computing system. And access to one memory address should not have unintended side effects on data stored in other addresses. I still believe this. I think we don't want to get rid of this fundamental invariant. And we said that you could take over an otherwise secure system and you could hijack a system by inducing these bit flips and constructing an attack. And while we were working on it, the real experts from Google Project Zero, they actually wrote this blog post where they said that they actually induced these bit flips and they were able to gain kernel privileges by inducing these RowHammer bit flips. This is a fascinating system security engineering work, I think. I'd recommend, if people are interested, you can take a look at their Black Hat presentation as well as blog post. So I'm going to copy and paste directly from their blog post over here. They said basically they learned about the problem from our work. They tested a selection of their laptops and replicated the problem. And they built 2 attacks, essentially. One attack takes over the Google native client. It's interesting, but maybe not as interesting as taking over the Linux kernel. Basically, they constructed this attack where they took over the Linux kernel as an attacker that's a user-level process. Basically, the idea is relatively simple. I'm not going to go into the system security engineering. System security engineering is a lot, actually. You need to do a lot of interesting things. But they were able to induce bit flips in the page table entries of the process, that's user-level process. And these page table entry points to the page table of the process itself. Now, if you're able to induce bit flips in your own page table, and if you flip the right bits, you can get write access to your own page table, basically. And they basically construct the attack such that they can maximize the probability of gaining write access to your own page table. That's the idea. I think it's beautiful, actually. It's fascinating. And all of the RowHammer attacks later that came work in a different way in terms of how they induce these bit flips to gain write access to the page table. Although there are some other attacks that leak information also. There's a classification of this in our retrospective paper that talks about it. But this is a fascinating attack, I think. And later this became famous as RowHammer, and I like this characterization by a hacker on Twitter. Basically, this person says, it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door that you were after. So if you're somehow stuck in this room, everything is locked, don't worry. Just start banging on the walls, and if RowHammer is in effect, magically some door will open over there. I'm not sure if it's in effect over here, but okay. So I'm going to, there's a lot of work in this area. I'm not going to talk about these works. This is based on a talk, longer lecture, clearly. If it were a longer lecture, I would cover some of these works. I find this fascinating. For example, if people figured out how to do a CL Flush 3 RowHammer, people said, okay, why do you need CL flashes? And then, yeah, they basically cause these bit cache evictions based on memory access patterns. Clearly, you can do that, right? You can construct an attack doing that. Okay, other people later showed that you can use memory duplication. Okay, I'm going to skip a lot of these since we don't have time right now. I'm going to pick one early one over here. I think it's fascinating, actually. Actually, I'm going to talk about some of them with pictorially. Okay, this is actually an interesting one because some of the first people who picked up on our work was these folks who did wrote the memtest 86, basically memory testing programs, right? You would run these programs once in a while if you want. But basically, after our work, they added a RowHammer test. They included this test 13. They called it hammer test. They didn't have it before. And I don't think their tests are the best, actually. I don't think they cover. If you took this program and if you think that by testing your memory using this, you would actually quality assure that your memory will not have RowHammer, don't rely on that, because I think these tests, it's still an open research problem how to figure out how to RowHammer in the best way. But after they actually included this test, they apparently got a lot of reports from people saying that what's happening to my memory. And they had to say this, basically. The errors detected during test 13, albeit exposed only in extreme memory access cases, are most certainly real errors. So they had to soothe people. Okay, and they talk about some solutions. Okay, so clearly there are a bunch of security implications. I'm not going to talk about it. But these folks showed that, for example, you could gain access to a remote server by doing RowHammer through JavaScript. I like this one a lot because these folks show that you could do it on an ARM memory controller, but more importantly, they released an app. You can download this app, I think, still. These are folks from Vrije University in Amsterdam. These are folks from Technical University of Graz in Austria. But these folks show that you could deterministically take over an Android operating system. You could download their app. What the app does is, app takes advantage of the predictable memory allocation patterns that happen in the operating system. So the operating system is predictable. So that you can fool the operating system by doing appropriate allocations of different sizes to allocate your own page table entry to a location that you know is vulnerable to RowHammer. Of course, they profile the locations earlier. And then you can take over the system that way. I think it's very fun. Once you have this bit flip, people actually can do a lot of interesting things. And similar folks accelerated RowHammer using GPUs, and you could do it through the RDMA interface. These folks actually did this through the RDMA, and they took over a remote machine that way. And these folks did the same thing, except they were a little bit late. They had to put their paper on archive, as opposed to publishing in a top conference. But they did the same thing, essentially. And this is actually more recent. These folks show that you can leak data. You don't take, maybe you don't take over the system, but you can leak data. Okay. And maybe this is one other attack that you have. Or this could be the solution. Hammering, yeah. Let's see. Okay, let's keep going a little bit, if you're okay with it. Not until midnight, but... Okay, so let me quickly talk about some of the causes of it, and then we're going to talk about some solutions. So what are the causes? I think there are multiple causes. It's actually not as simple. Coupling is a big part of the cause, as I discussed, electromagnetic coupling. Conductor bridges can get formed, and in extreme cases, hot carrier ejection that happens actually across word lines. And we've actually confirmed this with at least two manufacturers right now. That one is old over there. Although manufacturers were very reluctant to talk about it from the very beginning. They still don't call it RowHammer, I think. In DDR5, for example, or DDR going forward, they have some refresh modes, and even though those refresh modes are added to deal with RowHammer, they don't call the problem directly RowHammer. I don't know why. I think we should be more open to these things because hardware is going to be inherently reliable. I think, again, maybe I know why, actually. It's really the mindset problem. DRAM as main memory has been a perfect memory. People basically don't think of it as having errors, except for soft errors. Soft errors happen once in a blue moon, unless you go to space. Then it becomes prevalent. And as a result, people want to keep this abstraction for whatever reason. Whereas flash, if you look at flash, that abstraction is broken, right? If the flash chip has an error rate, and that flash chip error rate gets exposed to the flash controller, and somebody builds that controller to take advantage of it. That doesn't happen in memory. In DRAM, basically, DRAM folks somehow want to keep it as perfect. I think we need to actually change the mentality, and we need to actually open up the memory a lot more to the controller and the system to get rid of these issues. So if you really want to be secure, somehow we need to open up that part. Okay, so we did a lot of other studies using our infrastructure. This is actually all of the modules that we've tested. Let me give you some examples. So how close, from the logical address space perspective, from the addresses that you issue from the memory controller, how close is the hammered row to the victim row, or aggressor row to the victim row? And we found out that the address difference is 1. Basically, most of them are adjacent in terms of the addresses that are issued, row addresses that are issued from the memory controller. But some of them are not adjacent. Now, there are multiple potential explanations for it. The most likely explanation is that DRAM manufacturers do internal remapping of addresses for various reasons. Power, reliability, fixing the non-working rows is another reason. And that's why we get this non-adjacency. There is a very slight effect that RowHammer can affect, a RowHammer in one location can affect something farther down than the immediately physically adjacent one. But that's not the case in these chips. So basically, most aggressors and victims are adjacent, but that's not necessarily true always, logically from the memory controller's perspective. This will become important when you develop solutions. Because if you develop solutions that require the fact that you know the address of the row that you need to fix because it's being hammered, then you need to know this information somehow. You either need to reverse engineer your address mapping into DRAM chip, which is not easy, but people have done it also. But you have to do it on a per DRAM chip basis. Or you need to communicate more information from the DRAM chip to the memory controller, which I think is a better solution going forward, exposing more information, being more open about it. Okay, so this is interesting. Basically, we also asked the question, this is the access interval to aggressor. Basically, how frequently you access the aggressor. When do we stop seeing errors if you keep increasing the access interval between two hammerings? So this is not allowed in the standard. You can do 55 nanoseconds. So clearly, as you increase the access interval, or how frequently you're accessing the hammered row, you get rid of the errors. But you need to really increase the access interval to 500 nanoseconds to get rid of all of the errors. So simple throttling mechanisms that are naive throttling mechanisms are not going to work because they have a huge effect on performance. Okay. And these are real data from real chips, by the way. So this is the refresh interval versus the error count that you get. Three different manufacturers. I didn't explain the previous graphs, but you see the curves are the same for all manufacturers or similar. So this is the refresh interval. 64 milliseconds was the refresh interval that we had at the time. Clearly, if you increase the refresh rate or reduce the refresh interval, you will get fewer errors because you will be able to do fewer activates in a given refresh interval. And we asked the question, how much should you really reduce the refresh interval? And the answer was basically 7x. So if you actually, for the worst devices, if you want to get rid of all of the RowHammer errors, you want to increase your refresh rate by 7x. So clearly this is not a good idea because we actually want to get rid of refreshes as much as possible, right? Clearly you can fix the RowHammer problem by increasing the refresh rate. It comes at a big energy and performance cost, but we don't want to do that. Okay, so data pattern is interesting because this data pattern doesn't cause as many errors as this data pattern. Actually, this caused 10x more errors in order of magnitude. Why? There's a lot more coupling that you induce if you actually have different levels of charge in adjacent cells. Whereas here, you have same levels of charge, the coupling capacitances are much lower. That's the idea. Okay, so we also showed that this is a very different error mechanism than a retention error mechanism. Victim cells are different from leaky cells. Errors are not strongly affected by temperature, although we didn't test really extreme temperature ranges over here. Errors are repeatable, and that makes it a security problem. We saw as many as 4 errors per cache line. That basically rules out simple ECC. Although, keep this in mind. Actually, I have a lot of stories around these things, but I'll tell this part of the story. I gave this talk on RowHammer. Actually, it was a broader talk on memory in the International Symposium on Supercomputing in Frankfurt. And I talked about RowHammer, and the next talk was from Micron. It was one of the ABCs, one of the major manufacturers. And the person who gave the talk, he's actually a good guy, but he basically came up and said, the first thing he said was, we have a solution to RowHammer. It's called ECC. And I didn't say anything, of course. And I knew that ECC was not a solution. And even if it's a solution, it's not a good solution. And we will talk about that also. But basically, Simple ECC, as employed in memory controllers today, which is single error correcting, double error detecting, it cannot prevent all errors. Now, this is with the caveat also that our testing was not the best RowHammer attack. Now, we also knew that clearly someone would reverse engineer ECC and have a much better attack than other people could do. And this happened recently in 2018, basically. Folks from Vrije University in Amsterdam who were doing a lot of RowHammer research, they actually showed that on an ECC-capable DIMM, you can reverse engineer the ECC and you can actually take over the system, even if you have ECC in that system. So ECC is not a good solution. ECC, as it is implemented, is not a solution. But I also believe ECC is not a good solution. So what is ECC? ECC is adding redundancy to every single row, right? So that you have, whenever you have some bit flip in your row, you have some redundant information to correct the errors. Now, this is very heavy-handed. This is a really good mechanism for fixing errors whose causes you have no idea about. If you have a random bit flip, you don't know why things happen, this fixes that error. Here, you know exactly why you have a problem, right? Somebody's hammering you. So you have a much better way of fixing these errors, probably, much simpler than ECC. ECC is a very heavy-handed solution to this. So when I actually talk about reliability in my courses, I tell my students, resort to ECC only when you have no idea about what you're dealing with in terms of errors. If you know what you're dealing with, if you know the cause, then you can design a customized mechanism to actually fix the errors. Of course, if the cost of that customized mechanism is much higher than ECC, perhaps you should go with ECC. But in this case, the cost of the customized mechanism is much lower than ECC. Okay. Okay, so there are actually interesting things like this, basically. There are victim rows per aggressor. It's not one. It's more than one, as you can see. And victim cells per aggressor can be very high also. And as I said, cells are affected by two aggressors on either side. We didn't exploit it. I don't know why we didn't exploit it in our paper, but Google folks picked up on it and they exploited it, and they showed that you actually could RowHammer much better. And that's the paper that talks more. And we have a retrospective on it. Now it might be a good time. Yes, exactly, because otherwise we'll go until midnight. Okay, let's break right now and we'll talk about solutions. Okay, so we'll continue with the RowHammer. And let's talk about solutions. We talked about the problem. We talked about the causes, even though we didn't go into a lot of detail since we don't have time. I think solutions are really important also. We talked about ECC as a potential solution and refresh as a potential solution, and we kind of dismissed those, right? But I think it's important to recognize there are two types of solutions that you really need. One is immediate, because it's an immediate problem. It's out there. There are vulnerable DRAM chips everywhere, and you need to protect them somehow. And because memory controllers are not intelligent today, you have limited possibilities. If you had an intelligent memory controller that you could program, that you could push your own scheduling algorithm into or refresh algorithm into, you could solve this problem much more easily than the solutions that are going to be employed, as we will talk about in a little bit. On the other hand, long-term solutions, I think, are even more interesting because we can do the right thing in the longer term, because these are for chips that are not designed yet. Basically, to protect future chips. Clearly, we have a wide range of protection mechanism. And our paper talks about 7 solutions in total. And Para, which I'm going to talk about, is proposed as the best solution. It's already employed. A version of it is employed in the field. But I think there could be other solutions, as we will discuss in a little bit. Okay, so some better solutions. Make better DRAM chips. Good luck with that. That's not easy. So, but this is not, I think this is not something to be dismissed easily. The questions, for example, can you use better isolating material inside your word lines? It's possible to do things like this, but it comes at very high cost, usually. Also, area. It comes at a very high area cost as well. Clearly, we don't want to make the cells bigger. I don't think that's going to solve the problem. But this is, I think, not going to be easy. That's why we're at this problem. And in fact, I think the solutions are going to be much more important, because future chips, the minimum activation count that's needed to induce RowHammer is reducing as you reduce the size of the cells. As the chips become denser and denser, the minimum activation count reduces, meaning that RowHammer becomes easier to mount. So any solution needs to take that into account. Refreshing frequently, again, is not a good idea. Sophisticated ECC, as I said, is not a good idea, because ECC is not a good idea in general if you know the cause of errors and if you can fix the errors in some other way. I think access counter is also interesting. Access counter is count how many times you access rows, and let's say don't access those rows for some time, right? Or do something else once you figure out that a row is being accessed a lot, meaning refresh adjacent rows. That's a possibility. So these solutions all have downsides, except I think access counters can be optimized in some way. You need to be careful how to optimize it. In the early times, the solutions were very high cost. People, for example, proposed an access counter per row, which is not good in general because you may have a lot of rows in DRAM. But if you actually are intelligent about it, you could actually optimize the solution. So I'm not going to completely dismiss this solution, but I'm going to dismiss, well, at least currently dismiss some of these solutions because they're very costly in general in terms of either cost, performance, power, or cost and power. Okay, so I'm going to skip these because we already said that. If you want to refresh more frequently, if you want to get rid of every error, you want to actually increase the refresh interval by at least 7x. And we don't want that at all. So what is the solution that's employed in the field? Unfortunately, it's refreshing more frequently. So your memory is being refreshed more frequently right now because of RowHammer, essentially. So if you, this is Apple's patch. Apple was nice enough to reference our paper, saying that that's part of the cause of this issue. Well, actually figuring out the issue, we didn't come up with RowHammer clearly. We didn't create RowHammer. But basically, they say this issue was mitigated by increasing memory refresh rates. They don't say how much. I believe it's 2x. I believe it's not 7x, basically. It's not enough to get rid of RowHammer error. So this closes the vulnerability, but this doesn't get rid of the vulnerability. Because getting rid of the vulnerability is really expensive by just increasing the refresh rate. Imagine you have a security problem, and you're really increasing your refresh rate on across the board in your entire memory. But this is the solution that industry has adopted because there is no other solution that really makes sense. I mean, there are, of course, software solutions. You could imagine you could use performance counters to figure out how often some row is being accessed. Unfortunately, I don't think the performance counter infrastructure is low overhead and robust enough in existing chips that you can employ those software solutions with and sleep nice at night, basically. I think those software solutions, people have proposed these solutions. I think it's a good idea to look into how to enable them. But it's high overhead in general. And as far as I know, people don't employ it, but they increase the memory refresh rates. Of course, this is a bit old, so I'm going to show you some new solutions. So this was our solution. We examined a bunch of solutions in our paper, and we suggested this solution. I think it's very low overhead, but it has a downside, as we will see. So basically, this is called probabilistic adjacent row activation. The key idea is very simple. Whenever you close a row, meaning you activated a row, now you're done, you're closing it, you basically, with some probability, low probability, refresh, activate one or more adjacent rows. That's the idea. And if you choose a probability nice enough, then you get rid of the RowHammer effect. Of course, determining the probability is important. And if you're paranoid, you can increase the probability, but increasing the probability increases your refresh rate. Right? That's the idea. It's a probabilistic solution. It doesn't detect whether you're being hammered or not. It employs this targeted refresh whenever it's needed. Well, not whenever it's needed, periodically, based on the probability. So we show that you get a good reliability guarantee. That's much better than hard disk's reliability guarantee. And if you're paranoid, you can increase the value of P. So this is low power, low performance overhead. You can see the average slowdowns that you get because of this. It's much better than refreshing 7x, basically. And it's also stateless. Stateless in the sense that you don't need to keep track of rows. As a result, it's low cost and low complexity. Actually, you can implement this with 2 counters. And if you don't need to do it randomly, meaning your probability can be more deterministic. Let's say every n accesses, you do these refreshes. Then you can actually do this with a very, very low cost. And we argued that it's a good and low overhead solution. And actually, it's a version of this is done in DRAM chips today, but it's not perfect. So basically, you can do this in a DRAM chip or in the memory controller. In the DRAM chip, the way you can do this, you have enough slack and timing parameters, meaning the DRAM manufacturers tell you that they're spending, let's say, 350 milliseconds for refresh. That's what the data sheet says. But that's not true. They actually put a lot of margin to it. They're really spending, let's say, 200 milliseconds for refresh. I just made up that value, by the way. Meaning that there's 150 milliseconds of slack. And if inside that slack, they can do anything they want, actually. So this tells you 2 things. One is you're wasting performance because DRAM manufacturers are telling you these parameters that are highly guard banded. We're going to talk about that when we reduce latency. Reducing the latency will be possible by reducing those parameters. The second thing is they can actually do some things internally because they guard band things so much, which means that they can issue some more refreshes internally. And they do that somehow. I don't think it's perfect, frankly, but it's done in some DRAM chips. You can also do it in the memory controller. I think this is a better way to do it, actually. But this requires better coordination, better information passed from the memory DRAM to the memory controller. Because if you think about probabilistic adjacent row activation, memory controller should know which rows are physically adjacent to be able to issue the refreshes to those rows that are physically adjacent to the one that's being closed at this point. Now, if you know this is great, but this information doesn't get exposed to the memory controller today, and DRAM manufacturers tend to be very secretive about this because they think that exposing this information will give information about their circuit to somebody else, which means that their competitive advantage will be reduced. It's a bit sad, but that's the state of affairs. I think that needs to change going forward. I don't know how much time it'll take, but at some point it'll change, in my opinion. This is also exactly the reason. So DRAM manufacturers implement an ECC function, for example, in existing DRAM chips. That was not true when RowHammer was introduced, but current DRAM chips have simple ECC. It's actually a single error correcting ECC. But they don't tell the memory controller what ECC function they implement. So sometimes you get corrected bits, but sometimes you get some value from the memory controller, from DRAM, that goes through the ECC function. But if you have multiple bit errors, the value that you get is actually garbage. But you think that it may be a good value because you're not exposed to the fact that somebody is correcting these errors and they have miscorrected them. So it's actually not a good thing to actually not have that communication between somebody that's correcting errors here and somebody trying to make sense of the data that's coming out. Yeah, there's a lot of interesting issues over here. So this is the downside. Despite this downside, there are some recent Intel memory controllers that implemented probabilistic adjacent row activation. This is actually one of the Intel chips and BIOS associated with it. If you go to the BIOS, you can choose your RowHammer solution. It could be hardware RowHammer protection versus 2x refresh. If you go to hardware RowHammer protection, you can choose your activation probability of the adjacent rows. You can choose 1 out of every 2 times, which is not good probably. Or you can choose 1 out of every 211 times, right? Every 1024 accesses. After every 1024 closings of a row, you actually do the activation. Now, based on conversations with folks who implemented this, they don't have the information of which rows are adjacent here. They're banking on the observation that we made earlier, which is most rows are physically adjacent. If they're logically adjacent in the address space, they're going to be physically adjacent also. Which means that this closes most of the vulnerability, but you don't know whether you're closing all of the vulnerability. Okay, so hopefully this is interesting. I think there's still more need for RowHammer solutions going into the future, especially when so imagine a future where you can induce RowHammer with every 100 activates. And if you actually scale down too much, you may actually get there. 100 activates is not that much, actually. If you do 100, let's assume that you can do an activate every 50 nanoseconds. 100 activates is only 500 nanoseconds. No, 5,000 nanoseconds, right? Which is 5 milliseconds. Yes, you had a question?
What about the non-adjacent RowHammer? Because you mentioned before that
Yeah. So they're not as big of an effect, and they're not as repeatable from what we found. That's why we're not as concerned about them at this point. But again, there might be some time in the technology scaling future where that may become a bigger problem. But currently, as far as I know, people are not handling it as well as they're handling the adjacent ones. I guess the good thing about having refreshing everything is that handles the non-adjacent ones also. But it's a very high-cost mechanism. Actually, Para can be modified. We didn't write about it, but Para can be modified to do non-adjacent ones also, right? You could issue refreshes to non-adjacent ones at very even lower probability. Okay, so this is my takeaway. I think memory controllers need to be intelligent for security purposes, or reliability purposes, or safety purposes, however you would like to carve RowHammer as. And as I said, industry is writing papers about these reliability issues, even though they're not talking about RowHammer, but refresh, write latency, variable retention time, which we talked about. These are issues that were pointed out by Samsung and Intel as critical issues. And they basically argued for the same thing. If you actually have a smarter memory controller, you can improve these issues, like the variable retention time. Actually, this is a paper that mentioned that you should have ECC error correcting codes inside memory for handling variable retention times. Okay, so we've been doing a lot of experiments, as I mentioned, with flash memory. Actually, we built this infrastructure, this FPGA-based infrastructure for testing flash memory, NAND flash. This was planar NAND flash. We have another infrastructure for three-dimensional NAND flash. And I think it's fascinating. I'm not going to talk about this. We really don't have time for this. But this is an example of an intelligent memory controller that actually handles these reliability issues. Maybe not everything that you can imagine, but in terms of programmability, there's programmability in this controller. There's an FTL, flash translation layer. There's also a lot of mechanisms, different mechanisms to correct for different errors. There's a lot of ECC because there are a lot of random errors, but there are also different voltage optimization mechanisms that try to correct for errors by reading with a different voltage, for example. Again, I'm not going to talk about this, but we recently written this invited article at Proceedings of the IEEE on the work that we've done and also others have done in terms of what's happening in solid-state drives in terms of errors, their mitigation and recovery from those errors. This is also fascinating. I think flash is very nice in the sense that a lot of information gets exposed from the flash, or you can infer a lot of information if you know the interface and the right commands. But DRAM doesn't give you that information at all. So there's this disconnect between DRAM and the controller, whereas that disconnect is much more fixed in flash and the controller. So going forward, actually that 2013 paper that I mentioned, that International Memory Workshop paper, I argued for that DRAM becoming much more similar to flash in terms of its management. Maybe there should be a DRAM translation layer. That's really the intelligent controller, I think. And a DRAM translation layer can be beneficial for other things also. Imagine you have address remapping inside DRAM. You could do a lot of interesting things, actually. Okay, so I think the takeaway is main memory needs intelligent controllers to solve these reliability and security issues. Let's talk about the future a little bit. I'm not going to spend a lot of time on this one, but as I said, DRAM is becoming less reliable and more vulnerable, and I've already given you examples of this with this Facebook data. There's more data. Flash is also interesting. We've done similar study for flash if you're interested, again with Facebook. And also other problems may appear due to difficulties in DRAM scaling, or they may be going unnoticed. I'm very worried about these retention errors, for example. Some of them may be slipping into the field. Redisturb errors already, we know that they're slipping. Retention errors, they may already be slipping into the field, although they may not be as repeatable as RowHammer errors, because they're subject to these quantum-like effects, as we've discussed, like variable retention time. There could be read errors, write errors, and who knows what else. I think these errors can also pose security vulnerabilities if they can be taken advantage of somehow. So as I said, the data retention time errors, determining the data retention time of a cell or row is getting more difficult, and they may already be slipping into the field. And we've done a lot of studies. Again, I'm not going to go through this in detail, especially since we're running out of time. But there's a lot of studies that show that these errors are becoming much worse in scaled memory technologies. And one of the solutions that we've been proposing is to have a memory control that intelligently profiles memory once in a while. Basically, you try to figure out what is the retention time of each cell over the course of the lifetime. Initially, maybe you're refreshing everything very conservatively every, let's say, 32 milliseconds or even 8 milliseconds. But over time, you relax your refresh intervals because you know more about memory, and over time, you build confidence about your cells. And this way, you can also mitigate a lot of the aging effects that you may not be able to envision much early on. So that kind of online profiling-based memory control is, I think, a very good thing to strive for. We're getting there. So if you're interested, well, I already had this over here. If you're interested, these papers provide an overview. And this is perhaps the state of the art in terms of online profiling. But of course, as you mentioned earlier, when you do online profiling, whenever you're profiling a row, the data that you have over there is destroyed. So you need to move it somewhere. So there's overhead in terms of online profiling. The key question is, how do you actually overcome that overhead? Okay. I think that's what an intelligent controller should do. Okay, let's talk about how can we keep future memory secure or reliable. This is going to be more abstract a little bit. So we talk about DRAM. Clearly, there are a lot of errors in flash memory. But the emerging memory technologies have their own error mechanisms also. Basically, phase change memory, STT-MRAM, RRAM, memristors. They all have different types of errors. So for example, these are non-volatile memories, and they don't require refresh. But they require other things that resemble a refresh. For example, in phase change memory, in DRAM, charge leaks. In phase change memory, resistance drifts. Over time, the resistance values that you have drift. And if you don't have a large gap between one value and another in terms of resistance, then you may actually drift into the wrong value over time. So you need to really refresh phase change memory also. Actually, we were talking about this earlier. Flash memory also requires refresh over time, because what happens as you write into a cell, even though it's non-volatile, as you write into a cell, you wear it out, and you increase the retention loss that happens, at least in planar flash memory, even in 3D flash memory, but 3D flash memory is a little bit more complicated than that. But basically, if you've written to a flash memory, let's say 1,000 times, you need to start refreshing it if you want to make sure the data stays there, basically, for a long time. Of course, this depends on your retention time requirement also. If you keep writing all the time, then maybe you don't care. If you're not going to read it again, you don't care, maybe. But a lot of commercial-grade flash memory-based SSDs, what they do is, initially, they don't refresh flash memory. They keep track of how many times a cell has written. And if it passes a threshold, they start refreshing flash memory every 3 days, for example. Later, if you go into another mode where you start refreshing flash every 3 weeks. Later, you go into another mode, you start refreshing flash every I should have said every 3 months, 3 weeks, 3 days, and then 3 hours, and then 3 seconds. So the scale is very different from DRAM, but the refresh is still there. But of course, this has implications on flash memory being powered on also, right? If you have a refresh cycle, and if you're not powered on, it's not going to work. So this works very well in data center SSDs, but it may not work really well on your USB. So you should be careful about what you put on your USB. It may go away one day. And don't leave it under the sun also. Okay. Okay, well, I think we have a big challenge, basically. So the question is, how do we actually somehow design principled designs to prevent these issues? Can we somehow predict and prevent these issues? And I think, again, as I said, this is going to be high level. I believe there are 3 things that we really need to do. First of all, we should understand. Somehow we need to somehow find out these vulnerabilities and discover them and predict them before they happen. For example, I believe RowHammer could have been predicted if you actually had the mindset for this side of security, because you know that there is an error mechanism, and you could probably build a model to actually predict it. But I think the industry was caught off guard. It's an industry-level problem. It's not a manufacturer-level problem. Everybody was caught off guard, right? Because they were not really monitoring. They didn't have this mindset of monitoring for this type of error. And I think this modeling and prediction based on real device data and analysis is really important for this. We need to understand the vulnerabilities, and we need to develop reliable metrics. But this is not enough, because this enables us to predict, but this doesn't solve the problem. How do we actually solve the problem when it happens? This requires, I think, better architectures with security as key concern. So somehow we need to partition the duties better across the stack. DRAM should not be seen as perfect memory that handles everything, for example. Of course, while doing that, you cannot give up performance and efficiency. If your memory controller is intelligent, it shouldn't get in the way also. There's a reason why flash memory controllers are very intelligent. Well, depends on level of intelligence, but how you define it. But they're good at managing errors. The latencies are very long to flash. Whereas in DRAM, the latencies are at least an order of magnitude lower, or 2 orders of magnitude lower, actually. So you need to be very careful in terms of designing the memory controller when you do more in the memory controller in DRAM. And I think design and test flow need to change as well. Basically, how do we incorporate this sort of security and reliability vulnerabilities into the design, automation, and testing flow? I think a lot of testing needs to be online, as we mentioned earlier. But we still need to get high coverage and good interaction with other system reliability techniques. Okay, I think that's one of the reasons why we've been building the infrastructures, but I think there's more need for such infrastructures to really understand the problems. Okay, let me go back to this Galloping Gertie. The bridge was named Galloping Gertie because it was doing this basically for 6 months or so. And then it collapsed one day. Okay, but bridges are actually interesting. I like these analogies. Even though people have been building bridges for thousands of years, we still have these incidents, right? This was actually a lucky incident where there were no fatalities except for a dog. Here, there were fatalities. This is in Korea in 1994 over Han River. This is in Genoa, close to here. This is in Minneapolis. So these. Oh, okay, yeah, sorry. This is Minneapolis. Yes, that's Genoa. Out of order. Bit flip. Yeah, this Genoa. Maybe there's a newer one, but anyway. So basically, I think we have here, I think the solutions may be much more costly. But in computing, we have the ability to patch. Right? Here, we don't have the ability to patch as much, or patching comes at very high costs. But in computing, we know how to patch really well, especially in reconfigurable architectures, for example. I think in-field patchability is really needed to avoid such failures. And I think patchability goes really well with these intelligent techniques, right? Okay. So let me give you some final thoughts on RowHammer, if we're not doing too badly. Okay, I already said this, basically. Do I want to talk about Byzantine failures? Okay, maybe I'll talk about it. Do people know about Byzantine failures here? No? Okay. Okay, some people know. The professors know, it seems. Yeah. So Byzantine failures, you should take a distributed computing class if you want to know more about them. But this is actually a slide that I borrowed from Satya from CMU, who teaches a distributed computing class. He uses 3 things as examples of real-world Byzantine failures, and RowHammer is one of them. So basically, these Byzantine failures are... So the name comes from Leslie Lamport's famous paper, right? The Byzantine Generals Problem in Transactional Programming Language and Systems in 1982. And the problem is basically you have a distributed system and you have a bunch of generals and you're trying to attack a city and you want to capture the city. And some generals may be traitors, or they basically need to communicate with each other to decide when to attack. And the question is, how do you ensure a reliable attack when the messages between generals can be lost, either due to malicious behavior, some of them may be traitors, or due to somebody who's transmitting the message getting killed, right? Sorry for being clear, but that's essentially how the problem is set up in this case. And actually, Leslie Lamport goes on to prove that you need to have this much redundancy to actually ensure that the message, you can attack the city reliably in the presence of some number of traitors. You can read the paper. But basically, these failures are detected by undetected, or characterized by undetected erroneous computation. You have some computation, that is some error. The message doesn't get delivered. And this delivery doesn't get detected, right? And this is opposite of fail fast. Basically, you fail with an error or no result. And erroneous can be malicious also. Basically, intent is the only distinction. Basically, you have a bit flip that causes an error. It's a reliability problem, but it's also a security problem, basically. And it's very difficult to detect and confine these Byzantine failures, basically. If you have a Byzantine failure, the best way is really to avoid them. So RowHammer is an example of that. The best way is really avoiding them as much as possible. It's not good to think about a system where you have them and then you fix them. And that's the paper if you're interested. I go into more detail in my lectures, but that's the treatment here. Okay, I think I'm going to skip this quickly. You can look at it on your own. I think perhaps most importantly, what RowHammer has done is it enabled a shift of mindset in mainstream security researchers. Actually, I'll cover one story also. So people knew about the downsides of bit flips. This is not the first work that showed bit flips. Even in security community, people knew that if you get predictable bit flips, it's bad. And people knew that you could take advantage of it. You could take over a system. But no one really did all of these attacks because this was not, in a sense, real. Because what RowHammer enabled is it basically showed that a general purpose hardware is fallible in a very widespread manner. Its problems are exploitable from the software level. You can basically, at the user level program, you can induce a bit flip. So there's a paper from IEEE Security and Privacy in 2003 by Andrew Appel's group in Princeton. The paper is titled, I think, something like using memory errors to attack a virtual machine. What they do is essentially something similar to RowHammer. Of course, there's no RowHammer over there. But what they do is they go to a machine, they heat it up. They actually literally go with a light bulb, and they heat up the memory, and they induce errors. And they use those errors to actually take over the Java virtual machine. And they demonstrate that they could take over the Java virtual machine. They don't go enough to actually take over the Linux kernel, but the idea, once you have it, you could actually build up to there, right? So that's 2003. RowHammer is 2014. Between 2003 and 2014, this paper received a lot of attention, but no one actually went and really built up all of these attacks that people built up with RowHammer. I believe the reason was who's going to go and, if you have physical access to a machine, maybe you can cause a lot more damage than taking over the Java virtual machine, right? But with the RowHammer, because you can now cause those bit flips through software, even remotely, then you can actually do something much worse. So that's, I think, also another interesting mindset in also communities. The security community works this way. I think in general, software communities also work this way. If you cannot do something in software, it's not that interesting. Now, once it becomes something doable in software, it becomes very, very interesting, right? I think it's good to bridge that gap, of course, across the communities also, because imagine all of this work being done much earlier based on that paper, right? Of course, the downside of going and heating the memory of a machine with a light bulb or whatever heating source you have is you get a lot of errors. With RowHammer, you're very targeted, right? You cannot disturb the system as much. You don't disturb the system as much. Okay. Anyway, that's another story. So I think this mindset has enabled many system security researchers to examine hardware in more depth, actually. And they start understanding hardware's inner workings and vulnerabilities. And I believe it's no coincidence, and this is true for talking with these groups. Two of the groups that discovered Meltdown and Spectre heavily worked on RowHammer before. And they got really interested, are there other vulnerabilities? And now they went into and figured out that there are other vulnerabilities in hardware. Maybe harder to exploit than RowHammer, but they exist. Okay, I believe there's more to come over here. Okay, actually, if we go back and replay the slide, what I was saying over here is there's more to come in terms of RowHammer attacks, but it's going to be harder to develop these attacks because there are system-level solutions that are being in place. It's really a cat and mouse game now. So, for example, there's one solution that's called targeted row refresh. It's not para, but it's implemented in the memory controllers. I believe it's also vulnerable. So someone is going to reverse engineer targeted row refresh and say, this is implemented in some memory controllers. I believe there are some characteristics of it that make it vulnerable to attack. Someone is going to reverse engineer the operation of it, and they're going to launch RowHammer attacks with that. I believe solutions are also very important to examine going forward. So there's more to come over here. Okay. Okay, I think I've already talked about all of these. So bad news, RowHammer at the device level, physical level is getting worse. Good news, we have a lot more to do. So if you're really interested in RowHammer, I'd recommend reading the original paper as well as this retrospective. If you put them together, it'll be interesting. It was a lot of fun to write this retrospective. This was on a special issue on topics in hardware and embedded security. That was last year. Any questions?
You didn't mention anything regarding designing, let's say, chips that are shielded by design from RowHammer. Can you give us a
So I kind of mentioned that in terms of making better DRAM chips. I call that better. So you could do that, but it comes at a cost, basically. Because the question is, what is shielding in that case? You basically have more isolation across the rows, or you have different material.
So performance cost or production cost?
It's usually production cost, yes. You lose. You basically either need to go through new processes for manufacturing, or what was I thinking? Either new processes, or it has an impact on area because you need to isolate. Both of them, in the end, manifest themselves as cost. It's possible. It's not impossible, but people don't want to do it because that puts them back. This is like performance improving and at some point going back in terms of performance somewhere. Okay. Any other questions? Otherwise, I'm going to move to the third part.